All right, so last Friday we saw a little bit about covalent bonds and how to represent them with Lewis dot structures. We said anytime you have a small difference in electronegativity between two atoms, the bond's typically covalent, and that's where you share electrons, and it's normally between two nonmetals. So essentially what I mean, it's between two atoms on the right-hand side of the periodic table. So we saw the example with chlorine. We said if you jam these two together, each chlorine now has 8 electrons around it, which is good. Atoms like to have an octet of electrons. And then we showed the bonding pairs typically with a straight line, and then the lone pairs with single dots. And then we saw an example of ammonia down here where we did the same thing. And then I had a really important note that hydrogen's kind of the exception to the octet rule. It's okay only having 2 electrons. All right, let's try a harder one. This time we're going to go into multiple covalent bonds. So some atoms have to share more than 1 electron to maintain an octet. More than 1 electron in order to have an octet. So we'll take a look at a few simple examples with this. Let's take this one. Let's say we've got O2, so 2 oxygen molecules. How many valence electrons for oxygen? 6. So we can go ahead and say, all right, 1, 2, 3, 4, 5, 6. Makes sense. We've got 2 oxygen atoms, so I'll kind of mirror it on the other side. All right, when we go ahead and we try to pair this up, we can pair up those electrons that are unpaired. But now if we count the number of electrons around the oxygen on the left, for example, we'd say 2, 4, count both bonding electrons, so that'd be 6, and then the top one would be 7. We still don't have enough. But a simple solution is, hey, let's pair these electrons as well. Okay, so now when we go ahead and we redraw this, we'd say, all right, now it's actually sharing 2 electrons, or I should say 2 bonding sets between each oxygen, and each oxygen has 2 pairs of electrons left over. Can you see how oxygen on each side has 8 electrons now? Okay, so just like before, we can say, well, let's represent this using bond lines. So we've got 2 bonding sets, so we need 2 lines, and then we've got 2 lone pairs left over on each oxygen. So this would be referred to as a double bond rather than a single bond. Which do you think is going to be easier to rip apart, single bonds or double bonds? Single bonds. Double bonds, you've got a lot more electron sharing occurring, so it's a lot harder to rip these atoms apart. All right, let's do another one. Let's do nitrogen. So nitrogen is similar to oxygen. Instead of O2, it's N2. In fact, you guys did the breath lab, right, with the rusting? What did you notice about the percentage of oxygen in the atmosphere? What percentage was it approximately? Yeah, so just normal room air. Did you guys calculate how much oxygen was in there by percentage? Is the room 100% oxygen? No. If we lit a match and it were 100% oxygen, we'd blow ourselves up. So it's not 100% oxygen. Normally, atmosphere can be thought of to be about 20% oxygen. The rest of it's almost all nitrogen. So most of the air we breathe in is nitrogen. So let's try the same thing with nitrogen. We've got 2 of them, so I'll just put them side by side. How many valence electrons? 5, okay. So I'll go ahead, 1, 2, 3, 4, 5. I like to have my unpaired electrons kind of facing the other atoms because I know I'm going to have to link them up anyways. So I'll go 1, 2, 3, 4, 5 here. And then to pair them, we can say, all right, let's pair this one. And then we can pair this one down here. And then we can pair this one down here. Now we can redraw this using our dots. we've got 6 electrons shared in between those 2 atoms like that, right? All right. You can show this using a triple bond to show that there's 3 sets of electrons that are paired, and this would be the best representation. This would be a triple bond. All right. How many of you had a chance to listen to the Fritz Haber thing that I posted? Not sure if anyone did. That's okay. So on the website, I posted about Fritz Haber. Nitrogen is a really, really tough molecule to rip apart, right? So like I said, double bonds are stronger than single bonds. Triple bonds are even harder to rip apart. And the problem in the early 1900s was we need nitrogen to grow crops, right? So ammonia is used to fertilize crops. However, we were surrounded by this giant atmosphere of nitrogen. We just couldn't rip those nitrogen atoms apart to turn it into fertilizer. He was the chemist that helped to develop that process and won a Nobel Prize for it. So pretty interesting stuff. All right, let's try a harder one. And this time I'll give you a little bit of time to work on it with your partner. Let's do COCl2, and I'll give you a hint that carbon is your central atom. All right, let's try this as a class really quick. I gave you a hint that carbon's going to be the central atom here. So I'll just put carbon in the middle. I'm going to stagger the other atoms just around that central atom. So for example, maybe I'll put oxygen up here, and then I'll put 2 chlorines over here in each of the corners. So almost like a triangle of surrounding atoms. Make sense? All right, how many valence electrons for carbon? Say 4. So in group 4A. All right, how many for chlorine? 7. Okay, so 1, 2, 3, 4, 5, 6, 7. Like I said, I like to have the unpaired electrons kind of pointed towards the center because we know we're going to need to link those up. Okay, and then oxygen has how many? 6. All right, so now we've got to start pairing, right? If I focus on this chlorine on the bottom left, it only has 7 electrons, so it needs to definitely share 1 electron. So I'll just pick one of these electrons down here and say, all right, this chlorine is going to bond or share its electron with that electron on carbon. All right, same thing with this carbon over here. Say, all right, now that chlorine only has 7. If we pair up and share electrons, now it has 8. If we look at oxygen, it only has 6, so it needs to pair 2 electrons. So we'd pair this one, and then we could also pair this one. All right, so now if we go ahead, we can say carbon has 2 bonds to that oxygen. The oxygen still has 2 lone pairs coming off of it, so I'll stagger them like that. Then down here and here, we've got 2 bonded chlorines, each with 3 sets of lone pairs. And that would be the final structure. This is referred to as phosgene. It's used in the manufacturing of a lot of plastics, but it was also a World War I chemical weapon. Pretty nasty stuff. Does that make sense? All right, so part of your problem of the day is practicing these Lewis structures. Make sure you get started on that sooner rather than later. If you have questions, you can always stop by tomorrow morning before class. All right, so let's kind of switch gears and talk about polar covalent bonds. This is a bit different. And we're going to do a comparison. First thing we're going to look at is non-polar covalent bonds. And that's where electrons are shared relatively equally between two atoms. Between two atoms. All right, and so if you remember, we said if you look at the periodic table, the closer you get to fluorine, the more electronegative those elements are, right? And we said electronegativity is basically how badly it wants electrons. This is basically saying there's a tug of war between two atoms, but they're kind of the same strength, so one atom's not pulling and winning that battle more than the other atom. Make sense? Imagine two atoms playing tug of war with one another. The rope is your bonding set. It basically means nobody's winning the tug of war. So another way of describing that is that there is a small difference in electronegativity between those two atoms, meaning one's not going to win. And if you remember from math, delta just is the symbol for difference. It says this difference, if you look at an electronegativity table, is typically between 0 and 0.5, so pretty small. And let's take an example here. Let's look at a carbon-hydrogen bond. All right, let's go back to the electronegativity table and find carbon and hydrogen. All right, so over here we said that carbon is 2.5, hydrogen is 2.1, right? So that means the difference between them is going to be 0.4. Okay, so now we can go ahead and say the difference in electronegativity is 0.4. This bond is nonpolar. The tug of war is essentially even between that carbon atom and the hydrogen atom. Polar covalent bonds are a bit different. That's when you have a big difference in electronegativity. So let's make a note. All right. Polar covalent bond is when electrons are shared unequally. Unequal sharing. Typically, this occurs when there is a relatively large difference in electronegativity. Typically, this difference in electronegativity between two atoms is going to be around 0.5 to 2, give or take. I did want to make a note, though. If the difference is greater than 2, something else entirely happens. What do you think happens if there's a giant difference in electronegativity? Do you think they're even going to share? Yeah, it's just going to take one electron away from the weaker atom, right? So if that happens, what do we call those bonds? Ionic. All right, so let's take an example of this. The example I'm going to use is HCl. If we go ahead and draw the Lewis structure of this, it's pretty easy to do. Hydrogen has 1 valence electron. Chlorine has 7. That means chlorine needs 1 more. So we can really quickly draw this and say, all right, we've got hydrogen covalently bound to chlorine. Now let's go back to that electronegativity table, and find hydrogen and chlorine. So really quickly, we saw hydrogen is 2.1 here. And then if we go over to chlorine, it's 3.0. So now it looks like the difference is 0.9. That's a pretty sizable difference, right? So let's go back and say the difference in electronegativity equals 0.9. Chlorine is more electronegative. and I'll just abbreviate electronegative as En. Therefore, this bond is polar. All right, and chemists really like to show polarity using symbolic representations. So I'll show you how we represent bond polarity. So let's do this, bond polarity symbols. All right, so let's take a look at our example with HCl. We said that chlorine's more electronegative, right? So to show this, we show an arrow pointed towards the chlorine side. That shows chlorine's hogging electron density to the right-hand side of HCl as shown. And then we put a little plus end on the hydrogen side, basically saying it's getting electrons pulled away from it, so it's electron deficient, kind of partial positive in this example. So let's make a note. This is electron poor because it is less electronegative. And then this side is electron rich because it is more electronegative. It's winning that tug of war between the hydrogen and chlorine, right? All right. There's also another way you might see this. So I did want to show you both ways, especially if you take biology. Sometimes you'll see the same molecule, but instead of the arrow being shown, they use a lowercase delta symbol, delta positive for hydrogen and delta negative for chlorine. Same thing though. This just means electron poor, meaning partial positive or delta positive. And then this side is going to be electron rich, which means it's more electronegative. I'm fine with you using either of them in this class, and in your problem of the day, I ask you to show electron arrows, kind of like this. All right, so let's do a little bit of practice. Oops. All right, let's do ammonia and water as our two examples. So first thing first is draw the Lewis symbol and then determine which bonds are polar and then represent those polar bonds using appropriate arrows. All right, so let's try this as a group. We'll do ammonia first. We actually did this one previously, I believe on Friday. Ammonia normally has 5 valence electrons. Hydrogen, on the other hand, only has 1 valence electron, so we can stagger those around. And then really quickly we can say, well, nitrogen must pair its electrons with these hydrogens. So now we'll go ahead, draw the Lewis structure. And it should look like that. All right, so which is more electronegative, nitrogen or hydrogen? Say nitrogen, and let's just double check too. And don't worry, I'll give you this table on an exam if you need it. If we look at nitrogen over here, it's 3.0. It's in this kind of orange block. Hydrogen's normally 2.1, so that's a difference of 0.9. I'd say that's definitely polar. Okay? So now we can show each of these bonds using dipole arrows, or polarity arrows, where the nitrogen's basically tugging electron density away from all 3 of those hydrogen atoms. So it's got a 3-way tug of war, but it's winning the overall fight. Make sense? Let's do the same thing with water. And with water, oxygen's going to be our central atom. Got 6 valence electrons. We've got 2 hydrogen atoms, each with 1 valence electron. So now we've got 2 hydrogens, 1 oxygen. I'm going to pair these up. Now oxygen should have 8 electrons around it with 2 lone pairs. What's more electronegative, oxygen or hydrogen? Again, we can always double check our table. Say oxygen's 3.5 versus 2.1. It's a pretty big difference, 1.4. So it's in between that 0.5 and 2. So now we would show this using polarity arrows. Oxygen's going to be tugging from this hydrogen and from that hydrogen. So now we've got bond polarity arrows. Make sense? All right. Occasionally what I see though is students will show this a couple different ways, and that brings me into my next point. So there's a couple different ways that you could show water. So often Lewis structures don't show 3D shapes of molecules well. And I'll show you an example using our previous Lewis structure. We showed water like this, where each oxygen had lone pairs like that. But I've seen students where they will draw it like this, where they have the lone pairs on opposite sides of the oxygen, right? So if I were a chemistry student looking at this, I'd say, well, this angle right here looks to be 180 degrees, right? The hydrogens being on opposite faces of that oxygen. The one on the left, though, looks more like 90-ish. So then the question is, well, which shape is the more accurate representation of water? In this case, it's this shape over here. And we know this from experimental observation, that this bond angle is about 108 degrees. It's not 120 degrees, or sorry, 180. So we could just say this is the correct overall shape of water. So this leads into a theory that was really important called VSEPR theory. And so I'll walk you through what that means. Let me slide this down first, though. So VSEPR stands for valence shell electron pair repulsion. And this theory was really important. Basically says that electron pairs don't like being near one another. So electrons don't like being close to other electrons. Why is that? Yeah, exactly. So they both have a negative charge. If you put two negative charges close to one another, they repel each other. It's kind of like taking two like ends of a magnet and pushing them close to one another. It's just not going to happen. They're going to push apart. All right, so this led to a big theory saying that, well, we need to account for that when we're looking at shape. So I'll show you how to kind of use this key to your advantage. Specifically, we're going to start right here. So the key is that the number in that far left-hand column stands for the number of lone pairs. Whoop. The Wi-Fi here is awful. Number of lone pairs and bonded atoms. All right, so let's go back up and look at water, right? What we're normally looking at is the central atom. So in this case, with water, we have two bonded atoms, and then we have two lone pair sets, right? So that would be 2 plus 2. So 4 total electron pairing groups around it, right? Does that make sense? Oftentimes students say, well, why don't we count the individual electrons in the lone pairs? We just don't do that. We always count them as a paired group, right? So 2 lone pairs and 2 bonded atoms means immediately that we're going to be in subgroup number 4, right? And then if we go ahead and we look at the shape, does it look like water is tetrahedral? That's what the first one is. No, tetrahedral would mean you have 4 bonded atoms and no lone pairs, right? And then over next to that, there's trigonal pyramidal. That's 3 bonded atoms and 1 lone pair. And then last but not least, we've got bent, where it's 2 bonded atoms and 2 lone pairs. So in this case, water, according to this theory, should probably be bent, right? So it's going to adopt this 3-dimensional conformation. And if you look at the drawings, it's a little bit tricky. I'm going to zoom in. You see how they show a wedge there? So this wedge means that the lone pair is essentially sticking out of the board at you. And then this one over here means it's kind of going into the page a little bit. So imagine these 3 lower groups are like a bar stool leg, right? So you've got 3 legs kind of sticking down, staggered around in 3-dimensional space, and then this group sticking up. By adopting this conformation, everything's as far apart from one another as possible, right? So this would be the best descriptor for a water molecule. If we go over and we look at tetrahedral, can you imagine this kind of like with 3 bar stool legs and 1 piece sticking up? It's kind of confusing, but what you're going to do in lab on Wednesday is you're going to actually get a chance to play around with model kits and build things and see them 3-dimensionally in your hands. All right. Each of these subclasses, though, has a different electronic geometry. So let's make a note. Anytime you have 2 electron pairs, meaning down in this section, this is called linear electronic geometry. All right. So anything that falls in this subgroup, where we've got pink, that would be linear electronic geometry. That means you have 2 bonded atoms. They want to be as far apart from one another as possible, so they'll be on opposite sides. We don't have any lone pairs to deal with. The next one is trigonal planar. And that's where you have either 3 bonded atoms or 2 bonded atoms and 1 lone pair. However, these come in different flavors, right? You've got one that's just regular trigonal planar. That's where you have 3 bonded atoms. But if you replace one of those bonded atoms with a lone pair, now it's not really like a triangle anymore. The overall molecular shape would be referred to as bent. So the electronic shape would be, or electronic geometry would be trigonal planar, but sometimes the overall molecular shape would be called bent. All right, and then last one, we've got tetrahedral. And this could be any of the shapes within this class. So you could have tetrahedral, you could have trigonal pyramidal, or you could have bent. All of those are tetrahedral electronic geometries because you have 4 electronic groups around them. All right, the good thing is in this class, we're not going to do these. If you go on and decide to take general chemistry, you'll cover these, but we're not going to really worry about the lower level ones. Those get pretty complicated. Does that make sense? All right, it is kind of tricky though, so let's do a few examples, and then we're going to actually come back and talk more about polarity. Okay, so let's go back and just review what polarity is super quick. And we said that bonds are polar. If there is an imbalance of electron density. Essentially, that means one atom's winning the tug of war. However, oftentimes, we're not looking at individual bonds, we're looking at entire molecules. So molecules can have net polarity, also known as a dipole, if there is an overall imbalance of electron density. All right, so let's take some examples of this. And the first example I'm going to do is BF3, boron trifluoride. Let's do the Lewis structure first. And then we want to represent its 3D shape next. And then we're going to determine if there is a net dipole. All right, so let's do this one as a class, and then I'll let you do the next one on your own. Boron has how many valence electrons? 3. It's in group 3A, so we can really quickly draw 3 dots. We've got fluorine over here, has 7, so I'll stagger these around. And we know these will pair up, pair up, pair up. And in this case, boron's a bit odd. Boron is happy not having an octet. In fact, there's no electrons even available for it to have an octet, so it must be happy. So now let's redraw this using all of our lone pairs. All right, so if we look at boron, it has 3 attached fluorine atoms, so it must be in that 3rd subgroup. So if you go down to subgroup 3, what's the overall shape going to be? Oh, is that? Not quite. It's hard to see. If you look closely, 3 bonded atoms around a central one. Something planar, just not tetrahedral. Trigonal planar. Okay, so the 3D shape is trigonal planar. What should the bond angles be? It says right in the key. About 120. So really, I have it shown here with these fluorines 180 degrees apart from one another. That's not entirely accurate. We know that the overall 3D shape would be with 120 degree bond angles. So we'll make a note here that this is 120, and then the overall shape is trigonal planar. All right, so now what we need to do is determine whether or not there's a net dipole, and I'll show you how I do this. I'm just going to redraw this molecule over here with all of my lone pairs. First thing I do is I ask myself, are there any polar bonds in this molecule? So let's go check between boron and fluorine. So I'll go back to my electronegativity table. And boron is 2.0, fluorine's 4.0. That's a difference of 2. That falls in the polar region, right? So in this case, fluorine's going to hog that electron density. So I could show this using a dipole where fluorine is tugging on the boron. All right, now the question is there an overall imbalance of electron density? It's a bit weird to think about. Do you think one side of the molecule is going to have more electron density than any other side? Why not? Yeah, so you were saying that the fluorines are equally spaced around that boron and they're pulling at an equal intensity. Therefore, no side's really going to win out, right? So in this case, we would say no net dipole. There are individual polar bonds, but there's no overall imbalance of electron density. So no net dipole. They essentially cancel out. And in order to know if they cancel out, we have to imagine this in three-dimensional space, right? With 120-degree bond angles. All right, let's try a different one. Same thing, we'll do Lewis. We'll do NF3 this time. We'll do Lewis. We'll do our 3D shape. And then we'll do our net dipole determination. All right, so nitrogen normally has how many valence electrons? It's in group 5A, right? So it should have 5. Fluorine, we said, has 7. So I'll stagger those around. Okay, so now it looks like nitrogen needs to pair there, there, and there. Now nitrogen has 8 electrons around it. All right, so now if we draw it, oops, this should be fluorines, not hydrogens. Our Lewis structure says that nitrogen still has 1 lone pair, and we have 3 fluorines directly attached to that nitrogen. All right, so 3D shape. If we go to the key, nitrogen has 1 set of lone pair electrons, right? Plus 3 bonded atoms around it. So it would be in subgroup number 4, that tetrahedral electronic geometry. What would be the best 3D shape for this? What was that? Yeah, trigonal pyramidal. Okay, and if we try to draw this in 3D space, essentially each of these fluorines is going to act like a leg sticking down. And I'll show one of these fluorines coming off a wedge. That means it's coming out of the page towards us. And then the other one as a dash, meaning it's kind of going back into the page to give it a little bit of 3D perspective. And then the lone pairs just kind of hanging out right up here in this empty space. All right, so like I said, or like you said, this would be trigonal pyramidal, which makes sense, right? It looks like a little pyramid with fluorine legs sticking down, nitrogen's the top of the pyramid. All right, if we think about dipoles, we know fluorine's the king of electronegativity. It's going to hog electrons. So it's going to pull electron density away from the nitrogen in all of these directions. All right, do you think there's a net imbalance of electron density here? Yeah, I'd say so. The fluorines are all kind of pointed downwards. So the net average of all of those poles is going to be pointed directly down. They can't cancel out. They're pulling in the same direction. So let's copy this over. And then often what I do is I like to show a net dipole arrow. So in this case, I'll show the net dipole is kind of pointed straight down through the molecule. So it's an average of all of those individual polar bonds going in the down direction. So I'd say there is a net dipole pointed down, at least using this representation. Does that make sense? Really, we can't know whether or not polar bonds are going to cancel each other out unless we know the three-dimensional orientation of all of those groups. So it does take a little bit of time. Like I said, this is tricky stuff, so if you do need help on the pod, I'll be available tomorrow morning before class, and you're more than welcome to stop by. All right, I'll see you tomorrow.